Hi guys, I will be reporting the chapter 14 continuation of the waiting line model. Since we have already discussed the single channel waiting line and their uses and how to improve them, we will now be moving on to the multiple channel waiting line model with prolonged arrivals and exponential service times. This means that it consists of two or more service channels that are identical in terms of service capability, which is only in theory because in practice we can't really say that each service channel has the same or identical service capability. This is applicable only if the arrivals follow a zone probability distribution, and the service time for each channel follows an exponential probability distribution. The service rate is the same for each channel, and the arrivals wait in a single line then move to the first open channel for service. This is used by banks, diba? Example in BPI, when you come, if you arrive, when you arrive there, the guards will give you a number and they will just call you even though there are many service channels. The waiting line is still single. Next. It is also only applicable when the number of channels times the service rate is greater than the arrival rate, just the same with the single channel waiting line model, or when the arrival rate divided by the number of channels times service rate is less than 1. Okay, let's see. In our example in Burger Dome, diba, we have if we have one channel and we have a mean arrival rate of 0.75 and a mean service rate of 1, we would get the probability that no units in the system of 2.25. We have already discussed this last meeting. The average number of units in the waiting line is 2.25. The average number of units in the system is 3. The average time in the waiting line is 3 minutes. The average time in the system is 4, and the probability of having to wait is 0.75. So now we have two channels because we have multiple channels, and with mean arrival rate the same, mean service rate the same. We would get a probability that there are no units in the system of 0.455, the average number of units in the waiting line of 0.123, average number of units in the system of 0.873, the average time in line of 0.164 minutes, the average time in the system of 1.164 as compared kanina na 4 ba? 4 minutes. Nag-decrease na siya to 1.164. That's it. There are meron sa handouts na equation, so just look in here. Next is some general relationships. This is made by John B.C. Little, and we call it Little's law equation. So L is for the average number of units in the system, L sub Q average number of units in the waiting line, W sub Q average time a unit spends in the waiting line, and W average time a unit spends in the system. That is what you could get when you use these equations. Let's have an example. In a study of the grocery checkout counters at Murphy's Food Liner, an analyst computed that arrivals follow the zone probability distribution with an arrival rate of 24 customers per hour. So if there are 24 customers per hour, 24 divided by 60 minutes per hour is 0.4. Then, however, an analyst found that the service times follow a normal probability distribution rather than an exponential probability distribution. So Little's flow equation is also applicable if the Service time doesn't follow a exponential probability distribution. The service rate was found to be 30 customers per hour, so that's 30 divided by 60, 0.5. That is the service rate in the mean. A time study of actual customer waiting time showed that on average a customer spends 4.5 minutes in the system. So we already have W, the average time a unit spends in the system. We'll only have to get the W sub Q, the average time a unit spends in the waiting line, the L sub Q, the average number of units in the waiting line, and the N, the average number of units in the system. Using those equations, also known as the Little's law equation, we would get these. The average time a unit spends in this waiting line is 2.5 minutes. The average number of units in the system is 1.8 customers, and the average number of units in the waiting line is 1 customer. Okay, next. Economic analysis of waiting lines. Please identify the cost of operating the waiting line system and then base the decision regarding the system design on a minimum hourly or daily operating cost. This is applicable if you want to know what is more economical, using a single channel waiting line, a single channel service, or a two-channel service. In here we get the total cost with the formula of waiting cost times the average number of units in the system plus the service cost times the number of channels. The waiting cost is the cost per minute for a customer waiting for service, and the service cost is the relevant cost associated with operating each service channel. The waiting cost is harder to know because it is subjective. It isn't the same with the service cost, where you can easily assign the cost of service. For example, at Burger Dome, the cost estimated for servers' wages, benefits, and other direct costs is $7 per hour. We assume that the company is willing to assign a cost of $10 per hour for customer waiting time. What is the total hourly cost for single-channel and two-channel systems? Let us use the waiting line calculator, but there is also a formula, diba, kanina. In a one channel with a mid-arrival rate of 0.75 and a mean service rate of 1, kasi diba the example is from Burger Dome, so we're going to use this. And I've already put on the waiting cost and the service cost. So the waiting cost daw ay 10 and the service cost is 7. So 10, 7, we would get $37. If there are two channels, however, we would get only $22.73 per hour. So that is more economical and less costly. Therefore, to use two-channel waiting line system. Here's a graph. As the waiting line cost decreases, the cost of service capacity increases. So what we have to do is find the optimal capacity, or where the two lines intersect. Okay? Other waiting line models. This is developed by DG Kendall. Basically, this is just a denotion so that we wouldn't have to say single channel waiting line model with result probability distribution and exponential service time, or multiple channel waiting line system with Poisson probability distribution and exponential service times. Basically, this just shortens the term. So that is A slash B slash K, where A denotes the probability distribution of arrivals, B denotes the probability distribution of service times, and K denotes the number of channels. So for example, oh no, this is not example. M, this designates a presumed probability distribution for arrivals and exponential probability distribution for service time. D designates that the arrivals or service time is deterministic and constant, and G designates that the arrivals or service time has general probability distribution. These are the letters that you would substitute for A and B. So this is easier with example. For example, for a single channel waiting line with Poisson arrivals in exponential service time, that is MM1, because M is substituted for A for the Poisson probability distribution. M again is substituted for B for the probability distribution of service time. And 1 is for K because it is a single channel waiting line. If, however, there are two channels, that is M2. Okay. Next, single channel waiting line model with Poisson arrivals in arbitrary service times. The difference is the arbitrary. It is no longer an exponential service time. Retail sales at Hargur Lake's seafood supply are handled by one clerk. So that means there is only a single channel. Customer arrivals are random, so probably that is Poisson. And the arrival rate is 21 customers per hour. So 21 divided by 60. Oh, come on. 21 divided by 60 is 0.35. And the service rate, just its service time, is 2 minutes per customer. So that is 1 customer divided by 2 minutes is 0.5. And then with a standard deviation of 1.2, since this does not follow Poisson probability distribution and the service time is arbitrary, we would have a standard deviation. Don't worry, it is given. So what are the operating characteristics of this MG1? We use G as a substitute for B because G. It says here that it designates that the service time has a general probability distribution with a known mean and variance. Okay? So, what are the operating characteristics of this MG1 waiting line system? Look at your handouts and you will see the formula for this. So, the average number of customers in the waiting line is 1.107, the probability that there are no customers in the system, 0.3, the average number of customers in the system, 1.81 customers, average time a customer spends in the waiting line, 3.17, the average time a customer spends in the system, 5.17, the probability an arriving customer has to wait is 0.7. Next is single channel waiting line model with random arrivals and constant service times. So that is the same with Poisson arrivals. Because random is Poisson. The only difference, MD1, because it says here by date candle that D designates that the arrivals or service time is deterministic and constant since service time is constant, we use the D. The only difference here is the computation for the L. Yeah, the L sub Q. Look at your handouts again. It is the formula. There's only one formula, but it's hard to find. That's it. Next is the multiple channel waiting line model with Poisson arrivals, arbitrary service time, and no waiting lines. Meaning, there shouldn't be any customer waiting for service. So that is designated by the G candle as MGK. G because G. Designates that the arrivals or the service time is a general probability distribution with known invariants. When it's arbitrary, we just assume that there is a general probability distribution. Okay? So with black customers cleared, what are black customers? Black customers are the customers or the arrivals occurring when the system is full, therefore they are denied service and are not allowed to enter the system. The assumptions for the multiple channel waiting line model is that the system has k channels. The arrivals follow a zone probability distribution. The service times for each channel may have any probability distribution. The service rate is the same for each channel and an arrival enters the system only if at least one channel is available. If there is no channel available, he will not enter the system. There are only three operating characteristics for this. The probabilities that J of k channels will be busy. For example, there are three channels. The probability that only one channel or two channels will be busy. Then next is the probability that all k channels will be busy. The percentage of arrivals are blocked and denied access to the system. And the average number of units in the system. Let's have an example. Microdata Software Incorporated uses a telephone ordering system for its computer software products. Callers place order with microdata by using the company's 800 telephone number. Assume that calls to this telephone number arrive at a rate of 12 calls per hour. So that is 12. We didn't divide it by 60 because it's okay because it's many naman. And we're going to get the arrivals and the probabilities per hour and not per minute. So that is 12. Arrival rate is 12. The time required to process a telephone order varies considerably from order to order. However, each microdata sales representative can be expected to handle 6 calls per hour, so the service time is 6. There. Currently, the microdata has 3 internal lines or channels, each operated by a separate sales representative. Microdata's management wanted to know the percentage of callers being blocked from the system. If management's goal is to provide sufficient capacity to handle 90% of the callers, how many telephone lines and sales representatives should microdata use? It says here that currently it has 3 channels. They wanted to know if how many is the optimal channel so that they could handle 90% of all the calls. So that some of the some of the callers so that 90% of the callers won't be blocked. The probability that there that the callers will be blocked if there are only 3 channels is 0.21. So that is 1 minus equals 1 minus this. That means 79% still of the callers are only 79% of the callers are handled by microdata. However, using the equation in your handouts, if there are 4 channels, only only 0.0952 of the callers will be black. So that means equals 1 is 90% of the callers will be handled. So the optimal answer, the optimal channel, and the answer to the problem is that we should have 4 channels. Okay? And then the L, that is the number of units in the system. Is the number of units that will be PC. That is 1.8. That is the probability. Next, waiting line models with finite calling populations. That is MM1, the same as single channel, but there is a finite calling population. All this time, we are discussing waiting line models with infinite population, meaning the customers that can arrive are unlimited. Here, the customers are only limited. The assumptions are that arrivals follow a result probability distribution, the service times follow an exponential probability distribution, and the population of units that may seek service is finite. Example. The Colt-Mayer Manufacturing Company uses a group of 6 identical machines. Each machine operates an average of 20 hours every day. Wait, there is only 6 possible customers, so that is finite, diba? Each machine operates an average of 20 hours between breakdowns. So if each machine, that is 1 over 20, you will get 0.05. That is the arrival rate. With randomly occurring breakdowns, the present probability is used to describe the machine breakdown. One person from the maintenance department, so that means there is only one channel, provides a single channel for the 6 machines. The exponentially distributed service times have a mean of 2 hours per machine. So that is 1 over 2. The service rate is 0.5. There is only one channel. Using the formula, we will get the probability that no customers are 0.4845. Average number of customers 0.3297, the average number of customers in the system 0.8451, the average time a customer spends in the waiting line 1.279, the average time a customer spends in the system 3.279, and the probability that an arriving customer has to wait 0.51. So that's it. That is the whole chapter 40. What's really important here is that you would know the operating characteristic of your waiting line model, because here you would know the statistics. Example, the average time a customer spends in the system, you have 3 minutes and you are in a fast food business. The 3 minutes is very long if you are in a fast food business. So you should either improve your service or buy more advanced technology so that the service rate or the service time is shorter and the arriving customer doesn't have to wait. The end. Thank you for listening.